You think you know what gravity is. You've felt it your entire life. Right now, it's holding you in your chair, keeping your coffee in your cup, stopping you from floating away into space. You learned about it in school. An apple fell on Newton's head. He discovered gravity. Gravity pulls things down. Simple. Obvious. Completely, utterly, magnificently wrong. Gravity doesn't pull. Gravity doesn't reach out and grab you. There is no force yanking you toward the center of the earth. What you call gravity, what you feel pressing you into your seat right now, is something far stranger. You are not being pulled down. You are trying to move forward through time, and the earth is in your way. I know how that sounds. It sounds like I'm playing word games. But I'm not. This is the actual truth about reality, and it came from one man sitting in a patent office in Switzerland, daydreaming about elevators. His name was Albert Einstein, and in 1907 he had what he later called the happiest thought of my life. That thought destroyed 200 years of physics and rebuilt the universe from scratch. Let's start where Einstein started, with a very simple question that nobody had bothered to ask. Imagine you're standing in an elevator. Normal day, normal elevator, you're going up to the 3rd floor. You feel your normal weight pressing down on your feet. Now imagine the cable snaps. The elevator starts to fall. What happens to you? You start to float. You've seen videos of this. You've seen astronauts floating in space stations. You know what happens. The moment the elevator is in free fall, you become weightless. Your feet lift off the floor. If you were holding a cup of coffee, the coffee would float out of the cup in little wobbling spheres. You and everything in the elevator are falling together, so relative to the elevator, you're not falling at all. You're floating. Here's Einstein's question. How do you know you're falling? You look around the elevator. You see yourself floating. You see the coffee floating. Everything looks exactly, precisely, identically the same as it would look if you were in deep space, far from any planet, far from any star, where there is no gravity at all. You could do any experiment you want inside that elevator. Drop something. Throw something. Spin around. Every single experiment would give you exactly the same result whether you were in a falling elevator on Earth or floating in empty space a billion miles from anything. There is no way to tell the difference. None. Einstein realized this is not a coincidence. This is a fundamental truth about the universe. If you cannot tell the difference between falling in gravity and floating in empty space, then maybe they are the same thing. Maybe falling and no gravity are not two different situations. Maybe they're the same situation described two different ways. Now flip it around. You're standing in that elevator, normal day, normal weight on your feet. How do you know you're standing on Earth? You feel weight. You feel pressed into the floor. You drop something and it falls. But now imagine that same elevator is in deep space, far from any planet, and a rocket engine is attached to the top, pulling the elevator upward with a constant acceleration. You're standing on the floor of the elevator. The rocket is pulling the elevator upward, which means the floor is constantly accelerating up toward your feet. You feel pressed into the floor. If you drop something, the floor accelerates up to meet it, so it looks like the object falls. You feel weight. You see objects fall. Every single experiment gives you exactly the same result whether you're standing in an elevator on Earth or being pulled by a rocket in empty space. Again, Einstein asked, how do you know which one you're in? You look around. You feel weight. Things fall when you drop them. But you could be on Earth, or you could be in a rocket accelerating through empty space. There is no experiment you can do inside the elevator to tell the difference. None. This is called the Equivalence Principle, and it's the key to everything. Standing in gravity is completely equivalent to being accelerated. Falling in gravity is completely equivalent to floating freely with no forces on you at all. These are not similar situations. They are the same situation. Think about what this means. Right now, you think you're sitting still. You think you're at rest, and gravity is pulling you down into your chair. Einstein says no. You are not at rest. You are being accelerated. The surface of the Earth is accelerating upward into you at every moment. You are not sitting still. You are being constantly pushed. Wait, you're thinking. That's crazy. If the Earth is accelerating upward, why doesn't it fly off into space? Why doesn't the ground rise up and smash into the moon? This is where Einstein gets really clever. The Earth's surface is accelerating upward, but it's not accelerating through space. It's accelerating through time. Let me explain with another thought experiment, one of Einstein's favorites. Imagine you're in that elevator again, this time floating in deep space. The elevator is not accelerating. You're weightless. Everything is calm. Now you drill a small hole in one wall and shine a laser pointer through the hole, straight across the elevator to the opposite wall. The light beam travels in a perfectly straight line. It goes from one wall to the other without bending at all. You mark where it hits. Now turn on the rocket. The elevator starts accelerating upward. What happens to the light beam? The light still travels in a straight line through space. Light always travels in straight lines. But while the light is crossing the elevator is accelerating upward. By the time the light reaches the opposite wall, the whole elevator has moved up a bit. So the light hits lower on the wall than it did before. If you're inside the elevator, not knowing about the rocket, it looks like the light beam curved downward. The light bent. But light always travels in straight lines. How can both be true? They're both true because you and the light are using different definitions of straight. The light is going straight through space. You, accelerating, think straight means something different. To you, the light appears to bend. Now remember the equivalence principle. Standing in gravity is the same as being accelerated. If light bends in an accelerating elevator, then light must bend in gravity too. Einstein realized that gravity must bend light. Not because gravity is pulling on the light. Light has no mass. There's nothing to pull. Light bends because space itself is bent. This is the leap. This is where Einstein went beyond Newton. Newton said gravity is a force that pulls on things. Einstein said no, there is no force. Gravity is the shape of space and time. When you drop a ball, the ball is not being pulled down. The ball is moving in a straight line through curved space. What looks like falling to you is the ball following the natural shape of spacetime. Imagine you have a trampoline stretched tight and flat. You place a bowling ball in the middle. The trampoline sags. It curves down around the bowling ball. Now you roll a marble across the trampoline. The marble will curve toward the bowling ball, not because the bowling ball is pulling it, but because the surface it's rolling on is curved. That's what mass does to spacetime. The Earth, the Sun, every massive object creates a dip, a curve in the fabric of spacetime. And everything else, you, me, planets, light, moves along that curved surface. We're all just following the straightest possible paths through a curved geometry. Those paths look curved to us, so we invented the word gravity to describe the pattern. But there's no force. There's just geometry. This is incredibly hard to accept because you feel weight right now. You feel pressed into your chair. If gravity isn't a force, what are you feeling? You're feeling the chair pushing up on you. You're trying to follow your natural path through spacetime, which is to fall freely, to float, to move through time without any forces acting on you. But the surface of the Earth is in your way. The Earth is pushing you away from your natural path. That pressure you feel, that's not gravity pulling you down. That's the chair pushing you up. When you stand on the ground, you are being accelerated. Constantly. Every second of your life. The ground is pushing up on you with enough force to curve your path through space-time away from its natural trajectory. If the ground disappeared, if you were suddenly in free fall, you wouldn't feel gravity pulling you down. You'd feel nothing at all. You'd feel weightless. Because free fall, falling, is your natural state. That's what objects do when no forces act on them. They fall. This turns everything upside down. Newton said objects at rest stay at rest unless a force acts on them. Einstein said there's no such thing as at rest in the universe. There's only free fall, following your natural path through curved space-time. When you're sitting still, you're not at rest. You're being prevented from falling. Let's test this with an everyday experience. You're in a car. The car is driving down the highway at a constant speed. You're sitting in the passenger seat. You feel completely normal, no sensation of motion. Now the car suddenly brakes. You lurch forward. You feel thrown toward the windshield. What happened? Your intuition says the braking force threw you forward. But actually, no force acted on you at all. You were moving forward at highway speed. When the car brakes, the car slows down, but you don't. You continue moving at your original speed. It's not that you were thrown forward. It's that the car slowed down around you. The seatbelt then applies a force to slow you down to match the car. That force pushes you backward into the seat, and you interpret it as being thrown forward. Gravity works the same way. You think gravity is pulling you down because you feel weight. But what you're feeling is the ground pushing you up, preventing you from following your natural motion through space-time. If the ground disappeared, you wouldn't feel gravity increase. You'd feel it disappear. You'd feel weightless, because you'd finally be moving naturally. Astronauts in the space station are not in zero gravity. Earth's gravity at the altitude of the space station is almost as strong as it is on the ground. The space station is falling. It's constantly falling toward Earth. But it's also moving forward fast enough that as it falls, it misses the Earth. It falls around the Earth in a circle. The astronauts inside are falling with it, so relative to the station they float. They're weightless. Not because there's no gravity, but because they're in free fall. You could create the exact same sensation in an airplane. Fly the plane up, then point it down and let it fall. Cut the engines. For a few seconds, everyone inside would float, just like astronauts. Same principle. Free fall. The airplane and everyone in it are all following the same curved path through space-time, so relative to each other, they feel no force. Einstein loved this kind of simplicity. He loved taking what seemed complicated and showing that it was actually simple, just looked at from the wrong angle. Newton needed gravity to be a mysterious force that reached across empty space and pulled things together. Einstein said no, there's no mystery. Objects just move. They follow the contours of space-time the way a ball rolls down a hill. The hill isn't pulling the ball. The shape of the hill guides the ball's path. But if gravity is just the shape of space-time, what creates the shape? Why does the Earth curve space-time around it? Einstein's answer: mass and energy. The more mass something has, the more it curves the space-time around it. The Earth creates a bigger curve than a human. The Sun creates a bigger curve than the Earth. A black hole creates such a steep curve that even light can't escape once it gets too close. The equation that describes this is Einstein's field equation. It's one of the most beautiful equations in all of physics. It says the curvature of space-time is proportional to the amount of mass and energy present. Matter tells space-time how to curve. Curved space-time tells matter how to move. It's a feedback loop. A conversation between geometry and substance. Here's where it gets really strange. Space-time isn't just space. It's space and time together. When mass curves spacetime, it curves time too. Time runs slower near massive objects. If you stand at sea level, your watch ticks slower than if you stand on top of a mountain. Not much slower. Imperceptibly slower. But measurably slower. We've tested this. We've put atomic clocks on airplanes, flown them around, brought them back, and compared them to clocks that stayed on the ground. The flying clocks show less time has passed. We've put one clock on the ground floor of a building and one clock on the top floor and measured the difference. Time on the top floor runs faster than time on the ground floor because the top floor is slightly farther from the Earth's mass. This is not science fiction. This is not theoretical. GPS satellites have to account for this. They orbit high above the Earth where time runs faster than it does on the surface. If we didn't program the satellites to correct for this time difference, GPS would be off by miles. Your phone's map app works because Einstein was right about gravity warping time. Think about what this means for your life. Your head is aging faster than your feet. Not by much. Over an entire lifetime, the difference is measured in billionths of a second. But it's real. Time is not the same everywhere. Time is flexible. Time bends around mass just like space does. This brings us back to Einstein's original insight, the one he had in the patent office. When you're in free fall, when you're falling, you don't feel gravity. You feel weightless. This is your natural state. This is what motion looks like when no forces act on you. You are following a geodesic, the straightest possible path through curved spacetime. When you stand on the ground, you are not following a geodesic. The ground is pushing you up, curving your path away from the natural trajectory. You interpret this as gravity pulling you down, but it's actually the ground pushing you up. Gravity isn't a force. Gravity is what happens when no force acts on you. Einstein described this by saying that in free fall, you are in an inertial reference frame. You are not accelerating. You feel no forces. An astronaut floating in the space station is in an inertial frame. When you stand on Earth, you are not in an inertial frame. You are being accelerated upward by the ground. The force you feel is real, but it's not gravity. It's the resistance to gravity. It's the ground preventing you from moving naturally. Let's do one more thought experiment to drive this home. Imagine you're standing in a room with no windows. You drop a ball. It falls to the floor. You feel weight pressing you down. You conclude you're standing on a planet with gravity. But what if the room is actually a spaceship, accelerating through empty space at exactly 9.8 meters per second squared, the same acceleration as Earth's gravity? You drop a ball. The floor accelerates up to meet it. It looks like the ball falls. You feel pressed into the floor because the floor is accelerating into you. Every single observation is identical. According to Einstein, there is no difference. Not. You can't tell the difference. There is no difference. These are not two situations that happen to look the same. They are the same situation described in two different coordinate systems. Gravity and acceleration are two words for the same phenomenon. This is why Einstein's theory is called general relativity. It's general because it applies to all motion, not just constant speed. And it's relativity because it says there's no absolute distinction between gravity and acceleration. It depends on your frame of reference. To someone falling, there's no gravity. To someone standing still, there is. Both are correct. Both are describing the same reality from different perspectives. The reason this is so hard to grasp is that our brains evolved in a world of weak gravity and slow speeds. In our everyday lives, Newton's description works perfectly well. Gravity pulls things down. Simple. Useful. Good enough to build bridges and fly airplanes. But it's not true. It's an approximation that works when spacetime curvature is small and speeds are slow. When you get near something very massive, like a black hole, or when you move very fast, close to the speed of light, Newton's approximation breaks down. Spacetime curvature becomes extreme. Time slows to a crawl. Space warps and twists. And suddenly the truth matters. Suddenly you need Einstein. But even in your everyday life, even sitting in your chair right now, Einstein's description is the correct one. You are not being pulled down by a force. You are being pushed up by the chair, prevented from following your natural motion through curved space-time. Gravity is not what you think it is. So what is gravity? Gravity is geometry. Gravity is the shape that mass gives to the fabric of space-time. Gravity is the curvature of your path through the universe. When you walk forward, you're not just moving through space. You're moving through time. Your trajectory has a direction in time as well as space. Mass bends that trajectory. Not by pulling on you, but by curving the landscape through which you move. Einstein once said, "I have no special talents. I am only passionately curious." This is how he figured out gravity. Not by being smarter than everyone else, but by asking simple questions that nobody else thought to ask. Why does everything fall at the same rate? Why can't you tell the difference between gravity and acceleration? What does it mean to be at rest? These sound like childish questions. They sound obvious. And that's exactly why they're profound. The obvious is where truth hides. Einstein looked at the most familiar sensation in human experience, the feeling of weight, and realized we'd been wrong about it for centuries. The next time you drop something, watch it fall. It's not being pulled down. It's moving in a straight line through curved space-time. The earth is in the way. The ground catches it. And you, watching from your chair, are being held away from your natural path by forces pushing up through your body. You are not still. You are not at rest. You are accelerating every moment of your life, pushed constantly upward by the planet beneath you, prevented from following the natural curve of space-time that mass has created. What you call gravity is just the universe trying to make you follow the simplest path, and the earth insisting you take a different route. That's gravity. Now you know you were wrong. And isn't that wonderful? To discover that the most familiar thing in your life, the sensation you've felt since birth, is not what you thought it was? That's the joy of physics. That's what Einstein felt in that patent office in 1907 when he realized that falling is freedom, and standing still is force. The happiest thought, indeed,